All right, hello everyone. My name is Bryce Babinik, and today I'll be presenting an impressive example and a few techniques for overcoming weakness in the Z-axis with 3D printing. And if you're here watching this webinar, you've probably experienced this before where your 3D printed part splits or separates between the layers. And so my goal here today is to help pass along a few techniques you can use and hopefully to help expand the applications of where you can use 3D printing, with full confidence. So we'll start with the quick agenda before kind of getting into things today. And I think it's kind of funny because a lot of the time when we're making these webinars, we have a topic in mind already, and then we create, a problem that we use to help discuss the topic. And this one kind of happened backwards where I had a problem and I created the webinar to help me sort of learn and fix that problem. So I'm going to start sort of in the same order today where we'll talk about the challenge that I got faced with, and we'll talk about why that Z-axis weakness created this challenge, and then we'll talk about methods for overcoming the Z-axis weakness before moving on to actually experimenting with these methods. And you'll notice experimenting is in quotations here, and there's a reason for that, which I'm sure you'll understand later. And then, of course, after that, we'll sort of discuss the results and see the final reward for all of this hard work. So getting into the challenge, I think there's an example that most people have had experience with before to some level or another, but especially if you're in manufacturing. And it happens when you've got this really old machine and it has a part that breaks on it, and then you're just stuck waiting on replacement parts for days or weeks. And then there's just this thousands of dollars of money lost while the machine is down. And so maybe you have this idea to 3D print the part, but there's always this sort of fear and hesitancy to use it, especially with these big machines because of concerns about strength. And so for my situation here, I had to overcome some of those same concerns, and I had to use a couple of different tricks and some creativity. But I ended up with a part that I was fully confident in, and so hopefully I can pass along some of those tricks and help you guys out with some of your own projects, and just keep expanding the options where printing is a viable method. So without further ado, this right here is my end goal. And so I want to be up in the mountains, on my motorcycle riding around. And it's one of my favorite activities, so I'll try not to make this a webinar about riding motorcycles, but it's really unfortunate that I enjoy riding so much because I live here in Dallas, Texas, which is home of some of the most ridiculous off-ramps and on-ramps, just highway overpasses you've ever seen. We've got all the traffic you could ever want, and we have suburbs basically as far as the eye can see. And so I really like to pack up and travel if I want to actually go for a fun and scenic ride. And so my favorite spot is up in Arkansas in the Ozarks, which is about 5 hours away. And so I've started renting or borrowing trucks to get there, which is nice because it lets me load the bike, skip the boring highway, and then I have room for camping gear and food and whatever else I might want to bring, which made it extra exciting when I finally bought my own truck recently, which is this older Ford Ranger. And I think this thing is the pinnacle of pickup trucks, but that's another story. In the fall, it was finally time to sort of take this thing on its first trip with the motorcycle. And so I submitted a few last minute vacation days. I booked my camping reservation, and I thought I was all set. So I kind of just kicked back. But there was one problem I didn't realize I had until just a few days before the trip. And it's because I've borrowed trucks to do this in the past. So I have the ramps, I have the tie downs, I have everything I need for the bike. But it turns out to strap a bike down, you need a place to strap it to. And I had totally overlooked the fact that my truck didn't have any tie down anchors yet. Which didn't sound like the end of the world at first, because there are a ton of different ways to set up these tie down anchors. In my case, I have these existing threaded holes in the corners of the bed. And so if I can use those, it'd be awesome. Just because they're already there. And so I was planning to, buy these at first, but I ran into that same issue that you see with older machines because I have this older truck, and these things were just sold out everywhere. And the few that looked like they might have worked were just weeks of shipping time. And so I was running out of time, but I was talking to one of my coworkers, Kyle, at one point, and he asked me a funny question, which was, why don't you print one? And it's a great question considering where we work and all of this equipment we have. So, I had fallen into the same trap that we spend a lot of time trying to educate our customers around, where I had just totally written 3D printing off as an option for this part. One of the main reasons that I wrote it off is because I have this significant force, and I have that force in, different planes. And so I've got these bolts that are bolting this hook to the bed, but then I have the tie down hook that's pulling it in this weird angle. And so I just had this hesitancy to go and print this thing because I have these hooks holding a 400-pound motorcycle, which is my pride and joy, and they have to hold it in the back of this old truck while it's bouncing down the road for 10 hours. And then I'm also working in this really limited space. So I had just totally overlooked it. But that's, where materials and these industrial 3D printers really shine, because we have materials that are flame retardant, we have temperature resistant, and we have printers that can make insanely strong parts. But sometimes you just have to get a little creative with how you're making those parts. And before we get into resolving that problem, let's talk a little bit more about what my biggest fear for printing this part was, which is that Z-axis weakness. And if you've worked with printers before, you probably have some experience with this, but we'll elaborate really quickly on why it happens and what causes it. That way we can understand how to solve it. The scientific term to describe this characteristic is anisotropic, and it means that the properties of an object are directionally dependent. And a super common and natural example of this is with wood, where the strength changes significantly depending on where the grain of the wood is. So a quick visual for this: if I hammer against this little chip of wood within the grain and kind of distribute it across the grain, it'll be really strong. But if I try to split it between the grains, it'll break right apart because it's not as strong in that direction. When it comes to plastics, it really depends on the manufacturing process. A molded plastic part, for example, typically has uniform strength in all directions, but an FDM 3D printed plastic part is more like wood in that it's anisotropic. And that difference comes from three main factors. One is at a molecular level, where won't go into too much detail because I am not a chemist, but plastic polymers are made up of these repeating chemical chains. And so whenever the plastic is heated up or melted, the chains can kind of move freely and they get all tangled up together, which gives the plastic its strength. So if we visualize these polymer chains as electronic cords, for example, we can say molded plastic is like that drawer most of us have where we dump all of our cords that we never use but we can't get rid of for some reason. And all these things get all tangled together and it's totally impossible to separate one from the other. But 3D printing, on the other hand, we're melting one layer at a time as it comes out of the nozzle. And the previous layer gets heated a little bit, but not fully to melting temperature. So it's not as strong of a bond between the layers as it is within the layer. So it's like we took those cords and we tried to wrap them up individually, and then we put them in the drawer. They'll still get a little tangled, but it's still pretty easy to separate them when the time comes, one time a year when you need one of these cords. So that's one of the reasons for the weakness. The other two are mechanical, so I think it's a little more straightforward, at least for me. And it comes from that distinct lines that you see between layers in printing, and those create stress concentrations when force is applied, and they can also act as a sort of crack initiator, where the crack can then continue through the whole part because of our molecular weakness. And you couple that with the fact that FDM parts aren't typically solid filled, they use this sparse infill pattern, and so there's just less material overall holding the part together. So I've kept y'all waiting long enough. Let's finally start talking about options to overcome this weakness, and that way we can, take full advantage of our 3D printers. Steps 1 and 2 are relatively basic. Before you do anything, you really want to define the functional requirements for your part, and that's where you find out what the forces are that are acting on it, what are the magnitude of those forces, and what direction are those forces acting in. Because all of those things will come together in your decision for step number 2, which is determining what orientation you're going to print your part in, because the orientation determines a lot, but especially where those stronger interlayer bonds are going to be, and it also determines where your weaker Z-axis bonds are going to be. And so I always try to figure out orientation before I even get started modeling a part. Coming back to these motorcycle tie-down anchors that I need, when the bike gets strapped down, I know there's going to be this tensile force that's pulling on this loop at an angle, and then resisting the tension from that tie down are going to be the compressive force from these bolts. And again, because this is coming in at an angle, there's going to be a force on the walls of these bolt holes. And so those are all pretty big factors when I'm going to decide the print orientation. And so here's a couple of options that you can see, and you can kind of make your guesses as you want, and we'll actually see how this interacts later on in the experimentation side. But I can say that I wasn't fully confident in either option here for two reasons. And the first one is because that tensile force is going to be pretty significant, because at a standstill, maybe it just comes from the bike suspension while it's compressed, but during driving, that force is going to move around and it's going to be amplified by bumps and turns. And I know that for a fact because I worked on another webinar recently where I used simulation for 3D printing and I made a bracket for this motorcycle. And in that webinar, I rode around and collected data on G-forces while riding. And so I went to some pretty extreme lengths there to try and max it out. But if I'm trying to be a little more realistic here, I split the weight of the bike between the two tie downs and still have some G-force. I really confidently want to know that these things can survive at least 1,000 pounds, which by itself is already a pretty big ask from a 3D printed part. But in combination with that, I have a second concern, which is because these forces are acting in different planes, and that's where the sort of Z-axis weakness comes in, because there's not a print orientation that can optimize strength for all of the features of this part. So with option A, the bolt holes and the mounting flange will be really strong, but the hook is going to be more prone to breaking somewhere probably up here where it's a little bit thinner. And then option B has the opposite problem, where the hook will be really strong, but maybe it'll split somewhere between the layers where the bolts are, or it could just even potentially rip the hook completely out of the flange section. And that's where we can really start to take advantage of some of these different techniques to improve the Z-axis strength. And a couple of these techniques are especially powerful, but I'll start with some of the smaller ones where maybe they'll be helpful if the loads aren't quite as significant. And this is definitely a webinar about FDM 3D printing, but it would be irresponsible of me not to mention that SLA and SLS 3D printers have significantly better bonding between layers. SLA is actually considered fully isotropic because the layers are chemically bonded together in all directions. And SLS is somewhere in between the two in terms of interlayer strength. And then both of these options are fully solid filled parts as well. But coming back to FDM, this first one is really for any manufacturing process, and it's using fillets to help distribute stress concentrations. And for this example with the hooks, we could add a fillet between the hook and the flange part, which should add a reasonable amount of strength. And we'll actually see a good example of this in our experiments as well. The next one is just switching the material that you're using to print with. And generally speaking, you'll see better strength with nylon, for example, than with PLA. And part of that is at a molecular level where certain materials just bond better than others between the layers. In addition to that, you can get these fiber-filled filaments. And so this is a good example. This is Onyx from Markforged, and it's a nylon 6 with chopped up pieces of carbon fiber in it. And so during printing, when the plastic is melted, those fibers can move around and sort of reorient themselves, and they can get in between the layers and strengthen the layers as well. And so this by itself may not offer a huge improvement, but when you couple it with increasing your infill, it can actually make a pretty decent difference. Because if you have a material that bonds better and you have more of that material being bonded, it just increases your strength overall. So all these things so far are pretty straightforward, and they offer some improvement with relatively low effort. On the flip side, these other two things that I'm about to talk about offer a lot more strength, but you do have to spend some more time in CAD getting a little creative with your designing. The first is to take advantage of cheap and easy to get off the shelf hardware. And so a lot of the time you can just get stuff that's lying around the shop, because there is a phrase with 3D printing that complexity is free compared to machining. But there's a lot of great examples with this. And this one from Markforged is probably the best one that I've seen. It is a tube bending die where the printed part is this piece in blue, and then we have this tube being bent around the part. And there were two sort of major concerns with this thing. The first one is that when the tube is being bent, the pressure of the tube against the 3D print would split it in half along these layers. And then the second concern is because this piece in orange here are machine keys, and those are connected to a motor that transfers torque into this whole thing so it rotates. And so there's just this concern that it would shear and split the layers somewhere along where the machine keys meet the part. But they were able to overcome both of these things using off-the-shelf hardware. And so for the tube bending piece, they used bolts all the way around the curvature of this part. And those bolts are going to clamp the layers together and prevent them from separating. So you're kind of stealing the tensile strength from the bolts here. And then for the machine keys, they actually use these square dowels that press fit into the part. And the square dowels actually distribute the force between all of the layers all the way up into the part. And so it does a really good job of preventing that shearing from happening. So I think this part is a really good and impressive achievement overall, and they ended up with a fully functional part at the end of the day. So moving on to our last little trick here, we'll come back to these tie down hooks, and I sort of hinted at this a little bit earlier because we have these two options and I didn't really like either one of them, but if one orientation is good for the hook, one is good for the flange, and complexity is free, why not do both? And so for this example, the hook press fits into the flange. And so now with the flange, we have these bolt holes that are really strong, and we have this big opening for the hook. And then this actual flange itself is going to be much stiffer because it's printed in this orientation. And then the hook, of course, is going to be extremely strong because it's all printed interlayer here. And then we have this additional flat piece that will be kind of resisting the flange as the hook's being pulled. And so this technique adds a lot of strength just by itself, and it'll work with any FDM printer out there. But if you have a Markforged 3D printer, you can take things to a whole other level with this bonus tip, which is using carbon fiber reinforcement in each part. And that's because Markforged printers have a second nozzle that embeds continuous strands of carbon fiber into a part, and it irons that fiber into it. And so what you can see here is the X-ray view of our parts, where the blue is carbon fiber that's added inside of them. And these printers still have that Z layer weakness issue, but the fiber adds a ridiculous amount of strength within the layers. And so now these parts can be as strong as aluminum, and we just add the two of them together and we can take full advantage of the carbon fiber here. So here's a quick recap of our different techniques here. And it's a really good list. With these couple of things, you can make a pretty good difference on your prints. But one of the best things about this list is you can actually combine a lot of these things together. And so that's exactly what we did for the final version of this part. And here's kind of what it ended up looking like. I beefed up all the little parts of it just to start, and I increased the infill, and then I printed it out of nylon 6 with chopped carbon fiber. And then on the design side, I added this metal shackle that has a pin that sort of press fits into the part. And the pin did a really good job of distributing the force across the layers. And then the fact that it was such a tight fit means the part won't have to warp around the shape of the pin. And that'll make more sense once we go through the experiments for this. But the shackle was also nice because it rotates around the pin, and it just gives me more freedom as I'm hooking up my tie downs to it. And then I mentioned it earlier, but we have our two mounting bolts as well that are going to clamp these parts together and compress the layers. And then the last trick we talked about, splitting this up into two different parts and taking full advantage of each orientation, plus the addition of a couple of carbon fiber layers in each of these parts. And so in the flange, I've got some at the top and the bottom. So that's going to add a lot of stiffness with those sandwich panels. And it's also going to make it much harder for the hook to be pulled through. And then within the hook, I've got some layers striped out of carbon fiber just to strengthen the hook overall, and then give this piece that's going to be on the back side some extra stiffness so it can't get pulled through as well. But let's go ahead and take a look at what the experiments looked like for each of these different designs we've been talking about. When it came to the experiment, we had to get sort of as creative as we did with the design of this part because we don't have a big fancy Instron machine that we could have used to just pull this thing apart and seen what the actual readouts were when it happened. But what we do have is a big crane scale, gravity, and most importantly, a bobcat because of Kyle. So we can put all those things to work and we can actually do some science here. And I'll try to explain this using this super professional Photoshop diagram. So we're going to use the bobcat and we're going to lift it up. We're going to connect the top of the bobcat to our crane scale. And then the crane scale will be connected to two of the 3D printed hooks. And these hooks are bolted together. So we're actually kind of testing two at once here. And then the bottom hook is connected to some weight underneath it. So when the bobcat is lifted up, it's actually lifting this weight, and the crane scale will let us know exactly how much weight is under it, and it has a peak option that will track the maximum weight it sees. So if this part breaks, we'll know exactly how much weight it was lifting when it broke. Experiment number 1 is our vertically printed hook made out of PLA with 4 roof and floor layers, 2 walls, and 12% infill.
There we go, starting 20, 30, 40, 56 is where it broke.
56 kilograms, all right.
That's a benchmark. And it snapped right where we thought it would, right along the hook there, where it's really thin. Not too much grabbing on.
Yep.
So let's see how it compares. That sucked.
Test number 2 was the horizontally printed hook this time, still with PLA filament, 4 roof, 4 floors, 2 walls, and 12% infill. And the batteries for our tester died in the middle of this one, but we were still able to get a pretty close estimate.
Oh, hold on. 80.
Was it?
It was 80, yeah, right around 80.
Well, you said it was. Okay, let's
80 something. Though.
Let's.
Yeah. So you can see this one broke a little differently, and it actually broke along the hook. And that's probably because this is a really light infill. I think it's 10 or 15% with only a couple of walls.
Test number 3 is now our hybrid hook, which takes advantage of the strengths of each of the print orientations from our previous experiments, and the rest of the parameters are all the same.
30, 40, 50, 60, 70, 9, okay, 100, 110, 115. All right, that actually made it a lot further. And the hook survived. It actually broke along the flange.
Wow.
Interesting.
Test number 4 finally brings us to our fully optimized hook, and this is attempt number 1 to break this thing. It is a multi-piece design to take advantage of print orientations for both pieces. It's made of nylon with chopped carbon fiber filament, and then it has Markforged continuous carbon fiber reinforcement throughout the insides of this part. It has integrated hardware with the shackle and a pin to distribute the forces, 37% infill, 4 roof layers, 4 floor layers, and 2 walls.
All right, there we go. 20, 30, 50, 80, 100, 110. All right, we're past everything else so far. 160.
Breaking the log before we break the.
Really. 180. 190 and 200. We got the whole log off the ground, so this one survived. Much better.
All right. Well, we couldn't break this thing with a 400-pound log, so we're going to go for attempt number 2 to break it, and we're going to bump up the weight.
I made it through the last one with just the log, so now we have 2 railroad ties on here that are probably equal weight to the log. So we've got 3 times the weight, and we're going to see if it breaks. If it does, we'll get a peek on here, and we'll get an idea of exactly how much it was able to handle before it broke.
All right.
All right, let it rip out. All right, there we go. We got 2, 3, 10, 20. Slack right there. 80, 100. All right, we're way over where we were last time already. So we're at 300, 340, 350. 400. Jeez, it's gonna do it. 420. Yeah, it's warping in the middle there. 430.
Oh.
And it held that forks too. 435.
You can see daylight,
Yeah. 440.
and that's up.
It did it. 447 is the max, and you can you can see a huge gap between.
447.
But that carbon fiber is holding strong.
Get out of the way, log.
Jeez.
See if it looks anything we can see from this side. I mean, everything looks really good and solid.
Yeah.
So we still couldn't break this thing with 447 kilograms, which is 985 pounds. So we moved on to what was kind of our last resort, which was trying to pull a stump out of the ground and just trying to see where this thing would actually break.
Starting to pull, starting to separate, and now we have a break. 473 kilograms. Let's take a look and see what we lost here. So it looks like it broke in the sparse fill down here at the base of this hook.
All right. So the parts ranked pretty much in the order that we expected them to, but I know I was pretty surprised by how much each of them was actually able to hold. And I was also a little surprised by how some of them failed. So I thought it would be a good idea to include a quick discussion of what we saw. Starting with the vertical hook, this one is probably the only one that broke about where I expected it to, and that is the thinnest spot in the hook itself. And it just broke right between the layers there. And so that didn't surprise me, but it did hold a lot more weight than I thought it would. I was thinking maybe this thing would be 60 to 70 pounds, but it made it all the way up to 123 pounds. With the horizontal hook, I figured this one would be much stronger, but I was a little surprised by where it broke. I thought maybe somewhere in the flange it would be splitting between the layers or compressing or some type of failure there. But the fact that it broke along the hook means that increasing the wall layers here would have made a very big difference in what it could carry, but still made it up to 176 pounds. So still reasonably impressive for that one. With the hybrid hook, I was really happy to confirm that it was actually the strongest option when using the same basic print settings as a single part approach. But the failure did surprise me a little bit here as well. Although looking at it now, it makes a little bit more sense because one of the things we talked about was using fillets to reduce stress concentrations. And this was just a straight 90-degree edge here. So I'd be interested to know if filleting that edge would have made much of a difference. And it's especially interesting because when you compare that failure to the final part, it's very similar and it broke right off at that same edge. So I'll definitely consider adding a fillet there if I come across this situation again to see if that improves anything. But fortunately, this part passed the goal that I had initially set for it, which was being able to withstand over 1,000 pounds. And so I just printed another one and I put it on the truck and I was all set for my trip. So this is kind of what that trip looks like. And with that, we're at the end. So thank you guys for sticking around and watching this one. Hopefully you learned a thing or two. I know I definitely did, and I'm excited to use some of it in the future. But if you have any questions or anything, we're going to hang out here for a little bit. So feel free to enter them in now, and we'll be happy to answer them.